This is Catherine Nightingale with Chattanooga State Community College. This video is for Calculus 3 on the topic of cylindrical coordinates, section 14.7. Cylindrical coordinates are basically a 3D version of polar coordinates. We use them when a problem involves a cylinder, cone, or sphere, because it's often more simple to set up your integral for calculating volume in cylindrical or spherical, which video 2 will focus on, rather than Cartesian coordinates. So cylindrical coordinates are ordered triples with r, theta, and z. The r and theta are the polar coordinates for the projection of your shape onto the xy plane. Z is the vertical rectangular coordinate, and so you're just adding a third dimension to your polar coordinates in order to better calculate volume. You have the same equations relating Cartesian and cylindrical coordinates that you do when you're relating Cartesian and polar coordinates, except you have the added dimension of having a z function. When you're evaluating volume using a triple integral in cylindrical coordinates, you want to start by converting any equations for z into cylindrical coordinates using the equations above. And then you determine your r and theta bounds the same way you would in polar. So you project your shape down into the xy plane and it becomes a two-dimensional polar problem for figuring out your bounds for r and theta. Your volume differential will always be dz and then r dr d theta. We discussed earlier in a previous section why you have the r thrown in there when you're dealing with polar coordinates, and it's the same reason when you're dealing with cylindrical. So anytime you're setting up a volume integral, you'll have your volume equals your triple integral, and you'll have your dz r dr d theta, and your outer integral will come from your theta bounds, so theta has to have constant bounds. Your middle one will come from your r bounds, so r could be a function of theta or it could be constants. And your inner one will come from your z equations. So your z could be a function of r and theta, or it could be constants, or a function of one or the other of r or theta. Okay, let's look at a region that's bounded above by the paraboloid z equals 5 minus x squared minus y squared, and below by a paraboloid z equals 4x squared plus 4y squared. We want to set up a triple integral in cylindrical coordinates that will give the volume of D. Let's start by graphing our two paraboloids and seeing what the region looks like. I use quick graph to get an idea. So I have the blue one is the z equals 4x squared plus 4y squared, the paraboloid opening upward, and the purple one, the paraboloid opening downward, is the z equals 5 minus x squared minus y squared. So what we're looking at is that region where they overlap, or the area between the two. Okay, now the next thing I want to do is change my z equations to cylindrical coordinates. The first one, z equals 5 minus x squared minus y squared, I will write as z equals 5 minus the quantity x squared plus y squared. And that will just change to 5 minus r squared. The next one, z equals 4x squared plus 4y squared, I factor out the 4 and it becomes 4r squared. So I have my upper bound is the 5 minus r squared and my lower bound is the 4r squared. So those will be my z upper and lower bounds. Next thing I want to do is find the intersection in order to determine the r and theta bounds. So I have this intersection in either an ellipse or a circle, some shape like that. So what I want to do is just set my two equations equal to each other. 5 minus r squared equals 4r squared in order to find where they intersect. If I solve this, I get 5 equals 5r squared. Add the r squared to both sides to get this. And so r squared equals 1. Since r is always positive, I get r equals 1. So r is going to vary between 0 and 1. Last set of bounds I need are my theta bounds. Now if I projected that intersection down into the xy plane, I would get a full circle. And so my theta is going to range all the way from 0 to 2 pi. Since the intersection is a full circle, 0 is less than or equal to theta, less than or equal to 2 pi. Putting this all together, the volume is equal to outer bound 0 to 2 pi, then 0 to 1, 4r squared to 5 minus r squared, and then I want my standard integrand, dz r dr d theta. So to find the volume between those two paraboloids, I would find the integral given here. Example 2, we want to find the volume of the region in the first octant bounded by z equals square root of 1 minus x squared minus y squared, the coordinate planes, and r equals sine theta. So remember, the coordinate planes are where z equals 0, x equals 0, and y equals 0. So they've provided us with a nice diagram here, so you can actually picture what the shape looks like. It's bounded on top by a piece of a paraboloid, and on bottom by the xy plane. Okay, first thing I want to do is switch z to cylindrical coordinates, and z equals square root of 1 minus r squared if I do that, because x squared plus y squared is r squared. So since we're bounded by below by the coordinate plane, I'm going to get 0 is less than or equal to z, less than or equal to square root of 1 minus r squared. Now, next thing I want to do is find the bounds on r and theta. And to do that, I'm going to focus on the polar curve in the xy plane. So they've drawn it for us, r equals sine theta. I'm going to draw it in our normal xy plane so we can get a good look at what it's like. So it's like half a circle right here, going through the origin and going through y equals 1. So there's my equation, r equals sine theta. Now this first point on my curve is at the origin. Theta equals 0 right there. And with a little playing around, I can figure out that my curve is going to be traced out in this direction. And then at this point, sine of theta equals 1 when theta is pi over 2. And so that's going to give me the bounds that theta is between 0 and pi over 2. So now I have all the bounds that I need. R is varying between 0 and the function. Theta is varying between 0 and pi over 2. And so I get the volume is equal to 0 to pi over 2, 0 to sine theta, and 0 to square root of 1 minus r theta, and then my standard integrand. So what we have to do to find the volume is integrate this triple integral. Okay, so here's our integral. We have a whole slide to work through it. The first thing I want to do is integrate with respect to z. Since I don't have any z function, it just becomes the integral is just z, and I plug in my upper and lower bound. And so I end up getting r square root of 1 minus r squared as my new integrand. Now I have to use a u substitution for this. I'm going to let u equal the inner function. So u equals 1 minus r squared. So du, when I take the derivative, is negative 2r dr. And so in order to replace the r dr, I'm going to have negative 1/2 du. Integrating this on the side, I have negative 1/2 integral of square root of u, because I have square root of the 1 minus r squared. Du replaces the r dr. And so integrating that, I get negative 1/2 times 2/3 u to the 3/2. The 2's are going to cancel, so I get negative 1/3. So basically, what I have now, I still have the 0 to pi over 2, and I have negative 1/3. My u was 1 minus r squared. Raise that to the 3/2. Evaluate from 0 to sine theta. Plug in my upper bound and lower bound, and I bring the negative 1/3 out front. So now I have 1 minus sine squared theta, quantity raised to the 3/2 minus 1. So what I know is that this part is cosine squared theta. So it simplifies into negative 1/3 integral from 0 to pi over 2 of cosine cubed theta minus 1 d theta. Okay, now in order to integrate cosine cubed, I'm going to write it as cosine theta times cosine squared theta. And of course that minus 1 is just going to come along the whole time. So the cosine squared theta, I have a trig identity that tells me that's equal to 1 minus sine squared theta. So I'm going to have cosine theta 1 minus sine squared theta minus 1. Distribute that cosine theta. So I have cosine theta minus cosine theta sine squared theta minus 1. I'm going to do a u sub just on that middle part. So on the cosine theta sine squared theta, I let u equal sine theta, du equals cosine theta. So it becomes the integral of u squared du. So I get u cubed over 3. So it's sine cubed theta over 3. Okay, so what I have, negative 1/3, the integral of that whole expanded piece that I have over on the right, and I know that the integral of cosine theta is sine theta. I figured out the integral of cosine theta sine squared theta, and I know the integral of 1 is theta. So I get negative 1/3 sine theta minus sine cubed over 3 minus theta, evaluated from 0 to pi over 2. Plug in your bounds, and simplify. And we get pi over 6 minus 2/9. So that is the volume of this solid that we started with the picture of. So hopefully you're getting the hang of setting up your triple integral. The integration part is just what you've been doing all along with triple integrals. Work from the inside outward and using the same integration techniques as you learned in Calculus 2. Let's set up and integrate one more. Our next example asks us to find the volume of the region inside the sphere of radius square root of 2 and outside the cylinder x squared plus y squared equals 1. So I know that this sphere has radius square root of 2, and my cylinder has a radius of 1, so my cylinder is going to have a smaller radius. And I'm looking for this green shaded region inside the sphere and outside the cylinder. So you have this cylinder and this sphere intersecting it and just cutting out a chunk of it. My first step is to change my equations to cylindrical. So I have x squared plus y squared plus z squared equals 2. I can replace the x squared plus y squared with r squared. So that's what I'll start with. I have r squared plus z squared equals 2. If I solve for z, I get z equals plus or minus the square root of 2 minus r squared. So this tells me that my upper bound is going to be the positive square root because that's the top half of the sphere. The lower bound is going to be the negative square root because that's the lower half of the sphere. My bounds for z are only going to include the sphere because basically I'm not worrying about the cylinder with my z bounds. I'll take care of that with my r and theta bounds. So I just want to make sure I'm inside the sphere with my z bounds. So I have negative square root of 2 minus r squared is less than or equal to z, less than or equal to positive square root of 2 minus r squared. And this takes care of the inside the sphere part of the problem. Now, to find r and theta bounds, we want to project the region onto the xy axis, or xy plane. So if I just collapsed it all down onto the xy plane, basically I'd have a circle with a hole cut out of the center, and that hole in the middle would be radius 1. So I end up with my hole of radius 1 and my outer circle of radius square root of 2. That was the projection of the sphere onto the xy plane. So I just collapsed it all into a two-dimensional thing. So I have r is going to be between 1 and square root of 2, and since it's a full circle, I'll have theta between 0 and 2 pi. So I have all my bounds. Now I can set up my triple integral for volume. So I have theta from 0 to 2 pi, r from 1 to square root of 2, and z from negative root 2 minus r squared to positive root 2 minus r squared. So I get this volume triple integral, and my integrand, as always with cylindrical, is dz r dr d theta. Now, integrating with respect to z, I end up with upper bound minus lower bound. So I'll bring my r out front from the r dr d theta part. So I have r square root of 2 minus r squared plus square root of 2 minus r squared, because you're always subtracting the lower bound, and the lower bound's negative in this case, so it becomes plus. So that makes 2 of them. I'm adding them together, so there's 2 of them. So that becomes 2r square root of 2 minus r squared. I want to do a quick u sub on the integrand. So I'm going to let u equal 2 minus r squared. du is negative 2r dr. And so my integral becomes negative integral of square root of u du, so negative 2/3 u to the 3/2. When I plug my u back in, the 2 minus r squared, I get negative 2/3 2 minus r squared to the 3/2, evaluated from 1 to square root of 2. Plugging those in, The square root of 2 gives me a 0, and plugging in 1 gives me a 1. And so I'm basically integrating 2/3 from 0 to 2 pi. So I get 4 pi over 3. So that's the volume between the sphere of radius radical 2 and the cylinder of radius 1. So remember your steps. Figure out your z-bounds by switching your equations into cylindrical. Figure out your r and theta bounds by projecting your region down onto the xy plane and figuring out based on how you would in polar. And that summarizes cylindrical coordinates.